So, so basically, if I were to get a lever, or yeah, let's say I've got this lever and I've got a pivot, so it's going to pivot around this point here. In fact, let's make it neat. So I'm just going to make it a bit neater. So I've got a lever here, and what I want to do is I want to lift a big rock. Okay, so this is my rock. I'm going to color that in grey, and it's on this lever here. Now, to lift it, and let's just group this and rotate it. So it's down there now, okay? And I want to lift that up, okay? I want it to move up. Now to do that, what I can do is so I'm going to just zoom in here actually and make it a little bit smaller. So to do that, what I can do is I can push the other side down. And when I push the left-hand side down, the whole thing will rotate around this pivot in this direction, so anti-clockwise, right? So when I push this down, this side will go up and the thing will rotate by anti-clockwise. So now the opposing force is going to be the weight of this object here. So that, let's say the weight, which is equal to mass times gravity times the gravitational field strength. But for now, let's just say it's 50 newtons. So to oppose that force, you might assume I would apply a force of 50 newtons this way. In order to get 50 newtons going up, and then they would cancel out and the thing would move up. You would assume I would produce a force equal and opposite. But that is only if this pivot is in the middle. So if the seesaw was balanced, like the triangle, the pivot is in the center of the rod, of the plank, and we've got the rock on one end and me on the other end, then yeah, I would use the same force. But the distance from the pivot makes a difference. So in other words, if I wanted to push the rock up, but I'm not that strong, or maybe the rock's really heavy, what I can do instead is I can change where this pivot is. So if I move this pivot all the way down to here, and then I apply the force, I actually don't need to apply 50 newtons anymore to raise it. Maybe I only need to apply 10 newtons. So now the distance to the pivot is that distance there. Now that's the distance, we can say that's distance 1. And then you've got another distance, which is the distance that the rock is from the pivot, and that is to that center of mass there. We can call that distance 2. Okay, and then we would say that that force 2 is equal to 50 newtons, and then we can call this force 1 is equal to 10 newtons. So in other words, we've got two forces and we've got two distances. Now, so it and if you can try this out yourself. If let's imagine we're trying to open a paint lid with a screwdriver. That's a classic one. I'll get a picture to show you what I mean. So here we have the one that I actually ended up doing. The effort that the person is putting in, which is the force, is not as much as the load, which is the force of the thing that is being lifted. And then you've got the pivot there. And it's because it's got a large lever arm there. Same sort of thing is happening here. This one's a bit, it's often not properly explained. So let's just try to analyze this first of all. If I was to take a cross section of that paint tin, basically you've got a lip like that, and then it goes under, and then the paint lid, it goes like that, and then up. So we're sticking in a screwdriver through this gap here, and we're trying to get it underneath there, okay? And you can see then that is the pivot. So that means from using using the notation that I did before, that bit there is the distance 1, whereas this bit is distance 2. You can see that distance 2, the distance that the hand is going to be using, that's a much larger distance, and so when they apply a force that direction, the force that direction ends up being much larger. Okay, so this turning effect, in other words, how much of an effect your force has on turning something, we can call a moment. We can turning moment or moment, turning effect, turning force. Moment is the most sort of traditional type of word, and you calculate it by force times perpendicular distance. I've misspelled perpendicular there, haven't I? Oh, I haven't even put the P in. That was part of it. Perpendicular. I'm still not sure of that. Oh well. Perpendicular distance. So if we get let's get an animation up so we can demonstrate what I mean. So if we come over here then and we use this, open up this animation, this simulation. Okay, so let's put the ruler on here. What happens if I take that off and put mark on there? Oh, okay. Ruler, mark. Yeah, let's use marks. So same thing really. So there's the pivot, and then we've got 1, 2, 3, 4. We can imagine that's 1 centimeter, right? Yeah. So I'll use this annotation here. So we've got, let's say that's centimeter. Okay. Now, we know already that if I put 1 at 8, and if I put the identical ones there and remove it, it balances. And obviously, if we put them at different places, it doesn't balance. The reason why it balances at that place is because what we're going to do is we're going to calculate the total moment. So what we'll say is let's just decide that clockwise is positive. It doesn't matter. We could say anti-clockwise is positive. That's fine as long as we're consistent after that. To work out the moments, then you're going to go 5 times, and this is 8. It's 8 centimeters from the pivot. 8 centimeters. And because this one is making it go anti-clockwise, we'll do minus, and then it's going to be 5 times, and then it's 8 again from there. And you can see that these two are going to cancel out. And so it's 5 times 8, 40, minus 5 times 8, 40 equals 0. And so that's why when I do that, it doesn't move. The turning effect is 0. It has no effect on turning it. Okay, so the moment is 0. Yeah. Now, so let's do that again. Now, if I were to get that and then add that one there, now we will say, well, actually, this now means that the turning effect on the to make it go clockwise is going to be twice as much as it was before. So if I rub out that, so that's going to be 10 times. It's not going to be equal to 0 anymore because it's going to be 80 minus 40. So it's actually going to be 40. So the turning effect of 40, and the unit would be Newton centimeters in this case. So I should have put a Newton after 10 and a Newton after 5 there. So when I unlock it, it falls down to the right. Okay. But I can still balance this with the same masses. I would just have to reduce the turning effect on the left. So instead of having it multiplied by 8, I can have it multiplied by 4. And now I've got, oh no, wait a second, that's not quite right. Reduce the turning effect on the right. So the clockwise turning effect. So now I've got the turning effect on the right is back down to 40 because it's 10 times 4. And on the left, it's 5 times 8. That's still 40. So when I read, and then it balances out. So you can imagine this, they could make it a little bit more complicated, couldn't they? Because in this case, we've got two things pulling it down. And in these situations, the ones left hand of the pivot are always making it go anti-clockwise. The ones right hand of the pivot is always making it go clockwise. But I could apply some sort of upward force on the left hand side, and that would produce a clockwise effect, even though it's on the left hand side. So rather than thinking about left and right, you should get into the habit of thinking clockwise and anti-clockwise. And then, because you could even have, it could get even more complicated, and you could have like another thing here. You could have all sorts of things going on here. So let's come out of this, and I'm going. Let's just rub all this out if I can do it quickly enough, easily enough. I don't usually use this one because on Zoom you got Zoom Annotate, which is a bit easier to use than this one. But this one is a bit more slow and jerky. I'll just pause the video. Right. Oh, can I rub it out without? Yeah, I can. Okay, cool. And nearly that's last little bit there. Oh, and that bit there. So we now made a much more complicated situation. These two things are stuck together, and we can add all these moments together. So we got that distance, d1, multiplied by that force, f1, and then we've got this distance here, d2, multiplied by that distance, f2, and then we've got this distance here, d3, multiplied by this distance here, f3. And then we've got a red herring here, because this force, like pulling the actual thing, is not going to have any turning effect. So this, which we can call f4, will not have any effect, and they could catch you out with that. Imagine you were trying to turn this seesaw, and you just pulled that direction. It's not going to make it rotate. It's just, it might drag it off the pivot. But if we assume that, then if we forget about that part, then we can see that that's a red herring. That's not going to rotate it. So to work out the total turning effect here, you would go f. Let's say the total clockwise turning effect. You'd say f1 multiplied by d1, and then f2 is going to have an anti-clockwise. It's going to be minus f2 multiplied by d2. And then this one is actually a form of clockwise. So remember, so I'm doing this, look. So that one's clockwise. In fact, let's just color code them. Let's color code the clockwise ones. So that one, we'll do the clockwise ones in green, and we'll do the anti-clockwise ones in red. Okay. And there you go. So those two are causing a clockwise moment, and this is causing an anti-clockwise moment, and this is not doing anything at all. So, and then we're going to add F3, D3. So it may do something like that. Okay. Now another thing that comes up at A level is this situation. Let's imagine we had something, and this time we don't have a pivot. But we can still spin it. And everybody knows that if you put a pen on the table, which has no pivot, it's just sitting on the table, and I applied a force that way and a force that way, we know it's going to spin, and it will spin around that center. So this, if the force is, let's say it's 5 newtons, and this is 5 newtons, we know if we get our pen and then we push it up like this way and push it down on the other end, it will spin on the table. It will turn around. So this effect is called a couple. Okay, so the turning effect of those two forces to spin something around is called a couple. The other thing that we need to know about moments is it brings in it does come into play with center of mass and toppling. So if I get an image, what we're going to do is we're going to get a picture of an object on a slope. So I'm just going to get that now. So if we look down at here, we've got an object here of uniform density, which means that the center of mass will be in its center, and the weight would act down that. Now, the point at which it may topple would be this pivot here, and it doesn't topple because the weight is inside. We say it's inside the base, this bit here. Okay, so if it did rotate it, it would just hit another pivot, and that would hit on the ground there. At this point, the center of mass is going down the pivot, so this is at the point of toppling. Okay, it's just doesn't know whether to go anti-clockwise or clockwise. Okay. I don't want to use that one. Use Miro, not that. No. Right.
Okay.
I think we might have actually just reached the end of the lesson. I'm just going to wrap up this. It's okay. I've got a little gap, so I'm just going to wrap this up.
You've done 1 minute yet?
Yeah. Okay. Some objects do not have uniform density, which would mean that the center of mass may not be in the center. The center of mass could be top or bottom. Okay, so double-decker buses have a lot of weight at the bottom. A lot of their mass is at the bottom of their bus, and the top of their bus is quite light, relatively speaking. And it's also why bus drivers encourage people to stay at the bottom, because that way the center of mass of the bus is more along the bottom. So if anything were to happen, if they were to go around a corner and something went wrong, then the bus is not going to topple over because it's got a low center of mass, and so it's harder to topple. In this case, it's got a low center of mass. It's also off-center, which is kind of weird. But if it had a high center of mass, let's say high center of mass over here, and it dropped down, you can see that that's just outside the point, and so this would topple over if it had a high center of mass. So that's basically the overview of moments and center of mass.